In a previous video, we've been talking about linear alkanes and their associated stability and their flexibility. What happened though if you fuse the ends of those carbon chains together? What happens to the flexibility of conformations and the associated stability of cycloalkanes? Now do note that we are using cycloalkanes because they are a simple system to analyze, but you can extrapolate and apply these principles to a variety of cyclic organic compounds. When we draw cycloalkanes, we do so geometrically in a very 2D manner on a flat sheet of paper because, well, it is easier to draw them that way. However, they do not represent the true shape of the molecule. Remember that the geometry of a carbon is tetrahedral, so its angle should be about 109.5 degrees. However, if you look at the angles in these bonds, you will see that they deviate much from 109 degrees. For example, on the lower end here, with the triangle and the square, it is 60 degrees and 90 degrees. That's vastly different from 109 degrees. When we get to the pentagon shape, it's a little bit closer, 108. And the hexagon 120, and the octagon 135. So it seems that cyclopentane would be the only molecule that is happy because it doesn't deviate so much from the 109.5 degrees. Let's take a look at some energy data. If we compare the heats of combustion per CH2 groups, if we map the heats of combustion, we do notice that cyclopropane and cyclobutane, 3 carbons and 4 carbons respectively, have much higher heats of combustion, therefore much more unstable than the rest of the molecule in comparison. When you start to go to cyclopentane, cyclohexane, and cyclooctane, you see that the energy is much lower, so much more stable. So we see that the triangle shape and the square shape holds true to our prediction due to that deviation from the tetrahedral geometry. And in fact, that kind of strain has a special name. We call that angle strain. So then how come cyclohexane and cyclooctane does not have this angle strain? They seem to be very stable. And the answer to that lies in the fact that cycloalkanes aren't planar like the way we have represented them here. So in fact, when they are in a 3D shape, they can bend and twist themselves out of planarity and therefore can go into 109 degrees tetrahedral geometry. You can convince this to yourself by building this molecule, twisting and turning it until each carbon is tetrahedral. You can see it is possible. Whereas if you build cyclopropane and cyclobutane, you can see this being much more difficult. Also notice in the graph again, the lowest energy you can possibly get is when you have a ring structure with 6 members. There's a certain type of stability that comes with this amount of atoms in your ring, and so a lot of organic molecules do have this 6-membered ring system. So then let's focus on cyclohexane, and whatever applies to cyclohexane you can apply to other molecules that are similarly 6-membered rings. Hopefully you have had some time to play around with your model set to build your cyclohexane. As you do so, hopefully you will see some of the conformations that is possible for cyclohexane. It turns out there are 2 main conformations that cyclohexanes can adopt that will achieve tetrahedral geometry for every carbon. The first one is called the chair conformation because it looks like a lawn chair. It's drawn here as if you were taking a look at the ring structure from an angle, with the carbons in the front being highlighted darker, carbons in the back, just a simple line. Similarly, we can draw another conformation called the boat conformation. However, between these two, one conformation will be the more preferred conformation. It turns out that the chair conformation lacks this torsional strain, whereas the boat conformation still has that torsional strain. Also, now you see here the 2 hydrogens touching each other on top. That is a type of steric interaction that is only in the boat conformation. That steric interaction has a more specific name called flagpole interactions. Now, as you move from the chair conformation into the boat conformation, you can have many other types of conformation. For example, this is called the twist boat conformation, and this twist boat conformation is to alleviate some of that torsional strain from that boat conformation. So again, this chair conformation is the best conformation. However, there's two types of chair conformations. When you take the two carbons at the end of your first chair conformation, highlighted in red here, and pull the one that's on the right down and the one on the left up, you will also obtain a chair conformation. So in fact, there are two chair conformations that are possible. Because we are going to take a look a lot at cyclohexanes, you need to be able to draw these chair conformations. And again, the best way is to practice it. But here's one way you can start learning. First, draw a wide V, then from the top of that, draw a line down at that angle. And on the left-hand side, draw a parallel line. Then from that last one, draw a line going up, and then finally connect them. Notice that there are three sets of parallel lines in this chair conformation. We already saw that these two lines were parallel. Do you notice that these two lines are parallel? And lastly, these two lines are parallel. Notice that the parallel lines are two bonds removed from each other. So always make sure that the line that you're drawing has a parallel line two lines away. To draw the other chair conformation, we start again with that wide V. Instead of starting from the right this time, I start from the left, drawing from the left to the right diagonally downward. And so therefore, there's also that parallel line, and then completing that shape. Another way you can see how to draw a chair conformation is seeing that it looks kind of like a bow tie, but slanted either to the left or to the right to get either of the chair conformations. Any way you want to see it, the best way again is to draw it over and over again to get it good. Now I would say this one is a sloppy example, so I'm going to draw it again. That's a little bit better. Okay, so why do we need to know how to draw these chair conformations? Let's take a look at how to draw chair conformations of monosubstituted cyclohexanes. So I've drawn here a chair conformation with a substituent coming out of one of the carbons. I call that X. So if you go ahead and build this monosubstituted cyclohexane, you can see how different the substitute is oriented when you go from one chair conformation to the other. We are seeing the same molecule, but they look slightly different. And in reality, these two conformations are at constant equilibrium. They are constantly flipping back and forth between these two chair conformations. This equilibrium is known as a ring flip. So it's not like you're flipping a pancake, but you are twisting and turning a carbon-carbon bond to translate from one conformation to the other conformation. All right, so I just said that these two conformations exist in nature and they are going back and forth, right? But it turns out one conformation is more favored than the other. So for example, instead of just generic X, let's put in an actual group. Let's put in methyl. When a substituent is placed straight up or straight down along the axis of this ring, we call that an axial position. And on the other hand, when the substituent group is flayed out, pointing away in the same direction along the equator of the ring, we call that the equatorial position. So let's go ahead and analyze the conformation. So it turns out the structure on the right is much more favored. So at room temperature, you will find that 95% of the molecule will be in this conformation, whereas only 5% of this molecule will be in the conformation to your left. Why is this? The reason has to do with steric interactions. So let's go ahead and visualize this molecule from a Newman projection. We're going to go ahead and look down the Newman projection along these two bonds and these carbons being in the front. This looks a little bit different, but again, it's just a Newman projection of a fused ring. So if you were to fill in these bonds here, it might help us to see that there are hydrogens coming out here, hydrogens coming out here, hydrogens there, hydrogen there. So I'm just going to focus on these two CH2s right now. So with the carbon in the front, we notice that you have a hydrogen going up and a hydrogen going down. And this one is that. What about the right-hand side of this molecule? Again, hydrogen's going like that. So again, we have our back carbon and our front carbon. Focusing on the front carbon, we notice that it is connected in the front like so. Let's focus back on the left-hand side. The back carbon has a hydrogen going up and a hydrogen going out to the left. and then it's connected to a carbon like so. Now let's go on the right hand side again. The back carbon has a methyl going up, a hydrogen going out, and then the one going left is connected to the ring. And then the carbons in the center, I'm going to go ahead and write it as CH2. All right, so go ahead and take a look at this Newman projection. It's complicated, but if you just focus on this methyl group and this CH2 group, right? What is their relationship? Isn't that the same as a gauche interaction? And so indeed, that's a steric interaction, specifically known as a gauche interaction that we've seen in normal linear alkanes. And they do appear here too. So when they do appear in a ring structure, we give it a special name. It's called the 1,3 diaxial interactions. It's called 1,3 is because you have 3 carbons in between the 2 axial groups. And this 1,3 diaxial interaction varies depending on the group. The bulkier the group is, the worse the interaction. So for example, in a methyl group, only 5% of a methyl substituent will be in an axial position. If you change that group to a tert butyl group, a very, very bulky group, you will see that it really doesn't want to be in an axial position because of that 1,3 diaxial interaction gets blown out. So much that the preferred conformation dominates with 99.99%. All right, so now let's kick it up a notch. Instead of just one substitution, let's do 2 substituted groups on your cyclohexane. Let's take a look at this molecule, for example. When you have more than one substituent, the easiest way to represent the molecule is in this flat bond line structure with wedges and dashes. And as you recall, a wedge means it's coming towards you out of the plane of the paper, whereas a dash is going away from you. Now let's translate that into the chair conformation. So as I map this chair conformation, I like to number the atoms in my ring. The number on top I give as 1, then I go clockwise. So when I translate this flat structure onto my chair, my number 1 carbon, I always choose to be the farthest to the right. It doesn't matter which one you choose actually, as long as you are consistent about it. So I'm going to be consistent to the way I have learned it. So that carbon is number 1, 2, 3, 4, 5, and 6. Okay. All right. So notice this chlorine is wedge. Okay. So wedge means again that it's coming out of the paper. So if something's coming out of the paper and you have positioned your perspective to look at the side of this molecule, it looks like then it's rising above the ring, right? So to represent that on a chair conformation, the wedge is always up. Now there's 2 ways of drawing up. The first one is when your vertex at that corner is pointing up and your substituent is also up, then you're going to be in an axial position. Let's do a counter example. Remember there was this hydrogen here, right? Okay, notice that's on carbon number 2. So at carbon number 2, the vertex is pointed down. If it's pointed down, then I cannot have it in an axial position. It must be in the equatorial position. And how do I know how to draw this equatorial position? Remember there are 3 sets of parallel lines in the chair conformation? Well, your substituent, if it's in equatorial, will be parallel with one of the set that it is not touching. So in this case, at the vertex, I'm touching the red set and yellow set. So therefore, I'm going to be parallel with the green set. You see how that works? All right, so that's going to be your hydrogen. Let's go ahead and continue with the methyl group now. So the methyl group is on carbon number 2. It is represented by the dashed lines. So again, if you were looking with a perspective at the eye level of this ring, then something that's dashed would be going below the ring. So we will always represent it as down. So at carbon number 2, we need a methyl that's going down. Again, if the vertex is pointed down, then your down position is axial. When your vertex is pointed up, then your up position is axial. So there you have it. Again, just to contrast, let's draw in our last hydrogen over here. How would you draw in that hydrogen? How would that look like? It's at position number 1, and it's going down, right? And so the vertex is pointing up, so down must mean it's equatorial. So how do we draw equatorial? It must be parallel with a line that it's not touching, which is the red line. So you're going to be like so. So now let's try to draw the other chair conformation. So we got to flip this chair. Okay, so that's my flipped chair. Again, so we need to map this chair. So how I like to do it, my number 1 carbon is the farthest carbon to the right, right? So therefore, when I flip my chair, it's still going to be my farthest carbon to the right, which is this carbon here. So I'm going to name that number 1. And then everything else falls into place. Let's go clockwise here. 1, 2, 3, 4, 5, 6. Okay, so how about my chlorine? My chlorine, remember, is a wedge. So when you do a ring flip, you do not change the up or down position. If it's up, it stays up. If it's down, it stays down. So in this case, the chlorine was up. So at number 1 position, it is up. But notice now at the 1 carbon, the vertex is pointed down, whereas my substituent is in up position. So therefore, it needs to be equatorial. All right, so if it's equatorial, it's going to be parallel like that. And so that's how my chlorine will look like. Let's go ahead and fill in the hydrogen also. The hydrogen is down and the vertex is down, so it's going to be axial. Okay, let's go to carbon number 2. We got our methyl group. Our methyl group is down, but this time the vertex is up, so it's going to be equatorial. So that's what my methyl group will look like. Again, our hydrogen would be up and it's a vertex up, so I am going to have an axial hydrogen. All right, so there you have it. That's our 2 positions here. Now, if I had a question to say which of these chair conformations is more stable, how would you analyze this? Hopefully you were able to see that the conformation on the left has a methyl group and a chlorine group, both bulky groups, in axial positions. Whereas in the conformation on the right, the methyl group and the chlorine group is in an equatorial position, avoiding that uncomfortable, energetically costly 1,3 diaxial interactions, right? So you will most likely find the molecule in the conformation to your right. So if you were to draw an equilibrium arrow, you would draw it favoring the right-hand side. Okay, let's do another one for practice. What if we had this molecule? Can you draw the 2 chair conformations and also predict which chair conformation is the stable chair conformation? First, there's an ethyl group that is a wedge in carbon number 1. So at carbon number 1, wedge means up, so I'm going to have this as an axial position. And at carbon number 3, methyl is down. In this one, the vertex is pointing up, so therefore down must be the equatorial position. And it's going to be parallel with the line it is not touching, so it's that one. On the other side, we got ethyl group on the number carbon. Again, it must be up, but this time it has to be equatorial. And the methyl group is down, and this time it's axial. In this instance, we didn't have the scenario where both of our substituents were either axial or both were equatorial. In this one, you always have one that is in the axial position and one that's in the equatorial position. So there's a competition here, right? Let's highlight what I mean. So which one do you think will prefer least to be in axial? Ethyl is much larger, so for sure it will win in this competition to be in an equatorial position. So indeed, that's what you would have. The dominance of the ethyl group being in the equatorial position as a favored conformation. All right, and the last thing we want to talk about here is something called a cis-trans. When we talk about cycloalkanes, we often can give them these names. When you have substituents that are identical to each other, we can give them these modifiers. So the first one here is called cis, and you can imagine cis because both of these identical groups are in the same face. They are pointing up or wedge, whereas the second molecule we can call as trans because the 2 identical groups are in opposite faces of one another. One quick way to visualize this is through what we call a Haworth projection, where we kind of look at these 2 molecules on its side, right? And so the 3 bonds in the front is closer to us, so we're going to highlight them darker. Okay, and notice that the methyl group are pointed up, so we can draw them like so. versus the trans one. So this one methyl is above the ring and one methyl is below the ring. Notice in this projection, something that's above the ring and below the ring is very noticeable. And so again, that's called the Haworth projection. And you often see this when they talk about cis or trans molecule. All right, since we're here, might as well ask you then this question. Among these two molecules, which one is the more stable molecule? Is it the cis 1,2-dimethyl cyclohexane or is it the trans 1,2-dimethyl cyclohexane? So let's do their conformational analysis. So we have the cis conformation here. The methyl group is wedged, so it's up. The other methyl group is wedged, so it's also up. Again, it's going to have a chair flip where the methyl group now that was once axial becomes equatorial. The other group that was equatorial now becomes axial. Okay? Versus, so this is the cis side. What about the trans? So in trans, the first methyl group is up, the second one is down. Okay. And then this methyl group over here was axial and now becomes equatorial. This methyl group was axial, is also equatorial. Okay, so notice in the cis, both of the conformations are equivalent to each other because the one on the left has one methyl group axial and the one on the right has one methyl group axial. So it can't avoid having one methyl group axial. Whereas a trans structure, notice that the left conformation has two axial groups, but upon a ring flip, both of those methyl groups become equatorial. So it completely avoids putting a methyl in the axial position. So because of that, this compound is more stable. It can avoid that steric strain, that 1,3 diaxial interaction. All right, so that wraps up our discussion, our chapter on alkanes and cycloalkanes.